Okay then, everyone, we'll begin. All right, afternoon, everyone, once again. So I didn't see you in the lectures last week because Stephen took all the lectures last Monday to rebalance. So what's going to happen today is we are going to be doing sections 1.9 and 1.10. These are two applications, if you like, of partial differentiation, or two further uses that we can put it to. We're going to be looking at Taylor's theorem, Taylor series for functions of two variables, and also looking at how to find and classify stationary points of functions of two variables as well. And these two topics are the setting of some of the parts of my question on the coursework. I've got printouts of the coursework here, which I'll give to you at the end of this lecture. And then in my second lecture today, in the 5 o'clock one, we'll be doing more examples and problems related to Taylor's theorem or stationary points of functions of two variables. Okay. And in Stephen's lecture this afternoon, he'll introduce or comment on his part of the coursework as well. Okay. But before we get to that, we're going to have a look at sections 1.9 and 1.10 in the notes. So section 1.9 on Taylor series for two variable functions. So first of all, I just want to remind you of something you already know, which is about Taylor series of functions of a single variable. Okay. So we're going to recall the single variable case. So nice functions, the various technical conditions attached to this notion of nice functions, they have to be able to differentiate them, and I think probably the derivatives have to be continuous functions themselves. But we'll just take it for the moment that nice functions fx can be approximated near the origin by their Taylor polynomials. Or sometimes called their Maclaurin polynomials. And these are which are the finite initial parts of the infinite series. So this is an infinite series that gives you the value of the function. It's an infinite series, so it's a sum. It's an infinite sum. And it gives you a particularly nice standard representation of the function. Leave a bit of space in here for the coefficient, but this is an infinite polynomial series. Okay? So it allows you to express any nice function as a certain polynomial. So this thing as it stands is just the simple polynomial 1 plus x squared plus x cubed and so on. Of course, there is a coefficient here, which is comes from the function f. The coefficient here is f with a superscript in brackets evaluated at 0 and divided by the factorial of n, where f with the superscript bracket 0 refers to the nth derivative of f. Okay, it's a short, compact notation for the nth derivative, superscript in round parentheses. Okay. So if you know about the function f, and if you're able to calculate its derivatives, and you can evaluate them at 0, then you can form this infinite series polynomial, which gives you a nice expression for the function f. Okay? And okay, this is under certain conditions, certain nice functions. This is an equation. The function is equal to this infinite sum. But the idea is that if you take the finite partial sums of this, if you just take some initial bunch of terms of this infinite polynomial, then that will give you an approximation to the function. And the more and more terms that you take in, the longer the finite partial sum that you consider, the better the approximation to the function f. And okay, in general, this expression might only be valid near 0. So let's just say for an interval around 0. Again, this issue depends on the function. For some functions, this infinite series will only be valid for a certain region about the origin, for points close to the origin. But for other functions, they'll be valid. That expression will be valid across the whole of the domain of the real numbers. Okay, so that's something we looked at last year. So we would like to be able to, how does this extend to functions of two variables? Question mark. Okay, we have a very similar, it extends in a very nice way. Okay, so it's the structure of Taylor series for functions of two variables is quite similar. So we consider a function f of xy. We'll consider a general base point, AB. So we're going to be approximating the value of the function f evaluated at a point close to AB. We'll write h for the change in the x variable, k for the change in the y variable. Remember delta, capital Greek letter, delta is normally used to denote change in the variable. And it just simplifies the notation if you just use the single letters h and k for those two changes. And we'll write d for the differential operator. Now this quantity d is a combination of d dx and d dy. Okay? So d is a differential operator. Okay, so it's h times d dx plus k times d dy. And so this operator, capital D, is the kind of thing that you can apply to a function. Okay, so if you apply d to a function, f, say, it'll give you h df dx plus k df dy. Okay, and then in theorem 1.3, we can see the declaration of the structure of these Taylor series. So it says f evaluated at a point close to the base point. Okay, so you're evaluating your function f at a point a plus h, b plus k, and the structure is similar. We still have this 1 over n factorial part. We don't write the polynomial bits down separately because the polynomial bits are kind of contained in the application of, I'll put brackets around it here, the application of this differential operator to f. Now here we see the differential operator raised to a power. So what that means is, remember, d to the power n, d is an operator. So d to a certain power is going to denote the composition of n copies of d applied to f. So d to the power n applied to f, this will be d of, finally d of f. So you're composing the operator d a number of times applied to the function f. So you're building up higher and higher order partial derivative expressions in f. So d to the power n of f just means d after d after d after d of f, where in total you've got n d's there in that expression. So it'll be n copies of d. Okay, so that's what it looks like. So just to show you an example, I mean, what might d squared applied to f look like? D squared applied to f would look like d applied to d of f. Well, the operator d is h d dx plus k d dy. That's the outer copy of d. The inner copy of d is applied to f, so we've got h df dx plus k df dy. So this second bracket here is the differential operator d having been applied to f, h df dx plus k df dy. But then to work out d squared, we then have to apply d to the result. So when you expand out the bracket, so to speak, remember these are operators, so we're not multiplying these quantities together, we're composing the operations. But we do multiply the h's together, they'll multiply together to give h squared, but then you'll have d2f dx squared, because you'll be taking the x derivative of the x derivative. Then you'll have h times k, taking the x derivative of the y derivative. So that would be d2f dx dy. Then you'll apply the second term to the others. So again, you'll have hk d2f dy dx this time, because you're taking the y derivative of the x derivative. And then finally, you'll have the fourth term, which will be k squared d2f dy squared. But of course, Clairaut's theorem tells us that these two mixed second order partial derivatives are in fact the same thing. So we get h squared d2f dx squared plus 2 times hk d2f dx dy plus k squared d2f dy squared. Okay. and so on for higher powers of the operator d. d cubed applied to f would then be obtained by applying d to this expression here. So you get a combination of third order partial derivatives of f with respect to x's and y's, and multiplying each of them is a polynomial term in the h and k. Okay. So these are, the usefulness of this is it allows us to obtain polynomial approximations to two functions. Okay? So it gives you a nice standard way of representing functions. So this, at first glance, this doesn't look like a polynomial because you don't see the h to the k or the k or the h to the n or the k to the n, but they're embedded inside this object here. And when you evaluate it at the base point AB, that evaluates all these partial derivatives at the base point. So these partial derivatives all just take on a numerical value, okay? Because they get evaluated at a certain point in the domain. So you've just got various coefficients multiplied by these polynomial terms in h and k. So it's the polynomial in h and k which gives you an approximation to the value of the function at a point nearby to the base point AB. Okay, so where h and k are the offsets of the base point values of a and b for x and y. So we can look at a worked example to this, which is here in example 1.1 at the top of page 19. So here we choose a particular function. It's a combination of sines and cosines. So we're using f of xy equal to sine of x plus 3y plus the cosine of 3x plus y. And we're looking for the Taylor expansion or the Taylor polynomial approximation. There's different terms used, or you could call this the polynomial approximation of order 2. So we want to go up to order 2. So go up to second order partial derivatives, second order polynomial terms. So we're doing this function, and the base point we're choosing is pi over 2, 0. So x equals pi over 2, y equals 0. So what's the order 2 approximation going to look like? It's going to look like I wonder if I can fit it out. Let's put it. Well, I'm going to put it on this separate sheet, but you could maybe squeeze it on. So it's going to look like f at pi over 2 plus h. That's for the x coordinate. The y coordinate is going to be 0 plus k, so I'll just write that as k. Okay, so if we expand the formula up to order 2, the first term is going to be, well, it's going to be this. It's going to be j equals 0 up to 2 of d to the n divided to f over n factorial. So what that's going to come out as, when j is 0, you're going to have, well, 0 factorial is by definition 1. D to the power 0, what's that? Well, d to the power 0, d is an operator. So what's an operator raised to the power 0? It's you know, you're not applying the operator at all. Okay, so that'll just be the identity function. So that will just give you the partial derivatives are all evaluated at pi over 2, 0. So the first term here is just f at pi over 2, 0 itself. Because we're not applying the operator. So we've got d to the power 0. So that's the identity operator. So we just have the function f evaluated at pi over 2, 0. Then you've got the order 1 term, which is going to be h df dx plus 2, so plus k df dy. Again, these things evaluated at pi over 2, 0. So the two partial derivatives get evaluated at pi over 2, 0. That's the order 1 terms. Then the order 2 terms is our h squared d2f dx squared plus 2hk d2f dx dy plus k squared d2f dy squared. And again, it's evaluated at pi over 2, 0. Okay, so that's the full order 2 Taylor polynomial approximation to this f. Okay. Okay, these brackets get evaluated at pi over 2, 0, meaning these are the values for x and y that we feed into the partial derivatives to evaluate those to just numbers. So then it's a combination of polynomial terms in h and k up to order 2. So that is worked out on page 19. So we could have a look at what they do. So first of all, we're just looking at the function evaluated at pi over 2, 0. If you feed in pi over 2, 0, you find the value 1, because it's going to be sine of pi over 2, which is 1, plus cosine of 3 pi over 2, but cosine of 3 pi over 2 is 0. Then you look at the first order partial derivatives. Now, first order partial derivatives we could work out as well to add in there. So df dx, of course, is going to be cosine of x plus 3y minus 3 times the sine of 3x plus y. Okay, that's the x derivative, and of course the y derivative, you're differentiating the original f with respect to y. So this time you get 3 times the cosine of x plus 3y minus the sine 3x plus y. And when these get evaluated at pi over 2, 0, you get the values 3 and 1 respectively, because the only bit that generates, so 1 is going to be the sine of 3x. That's going to generate, well, sine of 3x, sine of 3 pi over 2 is going to give you a minus 1. So you in total get a plus 3 for df dx and a minus 1 for df dy. And so this is the order 1 contribution. This is the order 1 contribution to the Taylor approximation. Okay, so 3 times h times df dx, no, h times df dx plus k times df dy, but when you evaluate them, you get 3 and 1. So we end up with 3h plus k. Then going for the second order partial derivatives, okay, so we'd just be differentiating these expressions again. d2f dx squared, different pluses minus signs, with minus sine x plus 3y minus 9 times the cosine of 3x plus y, d2f dy squared, differentiating the y derivative again with respect to y, would give us minus 9 times the sine of x plus 3y minus the cosine of 3x plus y. And then the third second order partial derivative, d2f dx dy, you take the x derivative and differentiate it with respect to y, you have minus 3 times the sine of x plus 3y minus 3 times the cosine of 3x plus y. And so taking these 3 second order partial derivatives and evaluating them at the base point pi over 2, 0, we get these values, minus 1, minus 3, and minus 9, respectively, which is just picking up, see, the cosine of 3 pi over 2 will again be 0. So it's only the sine of 3 pi over 2 that is generating a value, and the sine of, it's going to be sine of pi over 2 this time. So sine of pi over 2 is 1, so we're just picking up this coefficient here, minus 1, minus 9, and minus 3. Okay. So the second order contribution to the polynomial, this is our h squared df dx squared plus 2 times hk d2f dx dy plus k squared df dy squared. You put in those evaluations. This is the order 2 terms in h and k, which go into the Taylor series. So putting all that together, then we get the conclusion at the end. It asks for the Taylor series up to order 2. Okay, so this is our approximation. Ooh, that's not an equal sign. Let's change that equal sign to approximately. Oh no, sorry. Sorry, I indicated ... that there was more to come. So sorry, you could leave it as an equal sign. If the ... dots weren't there, then you should have an approximation. Okay? The function isn't exactly equal to this polynomial, but it's approximately equal to it. But with the ... dots, you could leave it as the equal sign, I guess. Okay. So we get this nice order 2 polynomial in h and k that approximates the value of the function. So having these things is very useful. It gives you a standard way to represent functions. It gives us a way for mechanical computing devices to actually calculate arbitrary functions. Remember, computers are pretty dumb objects. Fundamentally, they can, all they can do really is just add and multiply numbers together, right? Go right down to the basic level of what the chips do. That's all they can really do. They can move numbers around, and they can add a 1 and a 0 and figure out that's 1, or add a 1 and a 1 and that's 0, modulate 2. So everything that computers do basically has to be built up out of multiplying and dividing. But this shows you now. That's not to say that when you ask MATLAB, when you evaluate some combination of sine and cosine with MATLAB, it mightn't actually be using the Taylor series. There are other related series which converge faster or are more appropriate for certain computations. But it is this kind of thing, this kind of theoretical tool that can approximate arbitrary functions, which we can imagine mathematically and build up the theory of mathematically, but ultimately they can be approximated by polynomials. And to work out the value of a polynomial, all you need to be able to do is to add and multiply. Yeah, because polynomial terms are just various powers of the inputs combined together. Okay? So you only need the fundamental operations of multiplication and addition to evaluate a polynomial, but that will enable you to approximately evaluate any function in principle. Okay, because functions can be represented by these good approximations. Okay. Are there any questions about that? Okay. So there are exercises in a few pages there in the notes. So we'll be looking at some of these in the upcoming tutorials, and I'll be doing example problems in the lectures. But that's basically the main idea for working with these. So the main thing to understand is this definition of the formula for them, where we understand that these are powers of the differential operator, capital D. Okay. Okay. The second thing we're going to look at this morning is section 1.10 here. And this is about extreme values of functions of two variables. Again, we're going to remind ourselves a little bit about the situation for single variables. It's best to explain this with just a quick look at the graph of a function. of a function of a single variable. So stationary points, sometimes also called critical points, or also called local extreme points, various terms used for these. These are locations where the derivative of the function is equal to 0. Now remember, the derivative is the graph, is the gradient, the slope of the tangent line to the graph. So we can see a few locations here. You can see a few locations here where the graph of this function, where the tangent has 0 gradient, meaning it's exactly horizontal. There'll be a point here somewhere. Okay. So there are these 3 locations here where the derivative vanishes at these points. F prime x equals 0. The derivative of f with respect to x is equal to 0. And we see all the different types of behavior exhibited here. Here we've got a local maximum of the function. Here we've got a local minimum of the function. And here we have what is called an inflection point. It's kind of a mixture of a minimum and maximum. If you look at the function just to one side, this is kind of acting like a local maximum. It's the largest value in a local neighborhood to the left of the point. Whereas if you look this way, it's kind of acting like a minimum. Because when you look locally away from this point to the left, this function is the minimum value locally. Okay, and those are the 3 possibilities for functions of a single variable. So for functions of 2 variables, where you've got, say, a z equals f of xy, the equivalent thing, stationary points or critical points, etc., these are the locations in the domain. So they're in the domain of the function, so they're points in the xy plane. Where df dx is equal to df dy, and where they're both equal to 0. Okay? So previously in the single variable case, it was where the first derivative of the function was 0. But now when we've got functions of 2 variables, of course, there are 2 first-order partial derivatives, df dx and df dy equals 0. This corresponds to the tangent plane to the surface. Remember, the equivalent thing to the graph of a function of 2 variables is a surface. The tangent plane to the surface, z equals f of xy, is horizontal. Okay, parallel to the xy plane, if these 2 partial derivatives vanish. Now, stationary points of functions of 2 variables are, again, come in 3 flavors, or 3 types. I'm going to attempt to draw some pictures of them. Yeah, that's pretty good. So you get points like this, which look like Again, this is a local maximum. It's a point that on the surface looks like the top of a hill, right? Imagine a nice smooth hill. On the surface, the summit of the hill, the very top point, is the highest point for a certain neighborhood around it. There might be higher hills elsewhere on the surface, but locally around this point, this is the maximum point. Okay, so it's a local maximum. Well, if you can have local maximums, of course, you can have local minimums. So this picture could be turned upside down, and you could have some kind of what you call I'm trying to draw here this kind of pretty good. Okay, these are all for pictures. We'll look at some more accurate pictures on MATLAB later on. You can have a local minimum, which is the opposite of the top of a hill, the bottom point in a depression. Okay, think of turning a hill upside down. Okay, so you can have local minimums. And the third type is kind of the analog to the inflection point that we saw for the graph of a function of a single variable. And these are so-called saddle points.
That picture is so unclear.
Yeah, well, okay, so what I was attempting to draw there was the opposite of a hill. So it's like a depression in the ground, yeah, which has a lowest point in the center of it. Yeah. We'll look at some better computer pictures later on. The third type of thing is it's maybe something like this. Okay, what exactly is going on here? So I'm talking about this point here.
That's a nice one.
That's a nicer picture, yeah. It is. Okay, so what I've drawn there is just a portion of the surface, just a bit of the surface. And this point is called a saddle point. It's called a saddle point because this could be part of the picture of a horse's saddle. Or if you imagine the saddle point on a horse, point to in the middle of the horse's back where the rider would sit, this is like a mixture of a minimum and a maximum. And this saddle point, if you go forwards, if you go left and right here, forwards and back along the horse, that point halfway along their back is like a minimum. Okay? The neck of the horse rises up in height. The rear of the horse rises up slightly from the middle of their back. Maybe not as much as that. Okay, but if you're looking this way, this point is acting like a local minimum. But if you go out of the screen and back into the screen, or down the two sides of the horse from the saddle point, of course the saddle point is like a local maximum. Okay, because the body of the horse falls on. Okay. So this is called a saddle point. And again, both derivatives of the function vanish here, and the tangent plane to the surface at this point will be horizontal. Okay? That's the third type of stationary point that you can have for functions of two variables. So we find the locations of these points by solving this system of simultaneous equations, okay? Okay. So the locations where both of these first order partial derivatives vanish, these are the locations of the stationary points. So we solve this pair of equations simultaneously. Okay, we find the solutions. They are the locations of the stationary points. The points are then classified into their three types using what's called the Hessian determinant. The Hessian determinant is this quantity which I've called D in the notes. And it's this determinant. It's the determinant of the 2 by 2 matrix of partial derivatives, second order partial derivatives of the function. Okay. So you got the 2 by 2 matrix of second order partial derivatives of the function, and you take its determinant. So it's equal to the product d2f dx squared multiplied by d2f dy squared minus the product of these two. But again, we know that these two mixed second order partial derivatives are the same for nice functions. So it's minus the square of that. Okay. And the way the classification operates, you can see it described there in the notes on page 20. The way the classification operates is at a stationary point, AB, so this is a point where both first order partial derivatives vanish. If D, when you evaluate D, if you get a negative answer, well, that implies that AB is a saddle point. If the value comes out positive, then you get, yes, question.
Is that the just the other side of it? Tell me how to that. The other side, it's where you said D2, dy2. Is it just D?
Oh, sorry. Yeah. Sorry. Yeah, should be dy squared. Thank you. Yeah, that's just a little mismatch. Yeah, second order, the y derivative 2 times. So if this Hessian determinant comes out positive, then the classification is based on the second order x derivative. You can actually choose the y derivative as well, which we'll explain. So if this is bigger than 0, then AB is a local minimum. And if it's less than 0, then AB is a local maximum. So it's like the single variable case where you locate those stationary points by solving the first derivative equals 0, and then you can classify them into local minimums, maximums, and inflection points using the second derivative of the function. It's a similar situation in 2 variables, except you've got a pair of simultaneous equations to solve, 2 first order partial derivatives, and you've got this, more complicated object, this Hessian determinant, which is this combination of the second order partial derivatives, and evaluating that at the stationary point, and depending on its value and the value of the second order x derivative, that tells you what type of stationary point it is. So what we've still got to do with this, okay, so that's just a quick run through the description of stationary points and a look at how they're classified. We got to look at lots of examples, or look at examples. So we'll start that this evening. We'll look at examples of finding and classifying these stationary points. And second thing to do is to explain or prove the classification by by the Hessian determinant. So why is it that if the Hessian determinant is negative, we've got a saddle point, and if it's positive, we'll have a local minimum and maximum. Okay, so there's some explanation to do there. Okay, so I'm just going to hand you out some paper copies of the coursework. It will be up on Moodle as well. And we'll discuss it and introduce it a bit more in the coming lectures.
Changing with respect to x and y is equal to with respect to y then x.